want to officially welcome everybody. Today's webinar presentation is brought to you by the IEEE Standards Association. My name is David Stankiewicz. I'm your event producer for today's session on UPFC technology and project application. We have a great guest speaker today, Dr. Yi Yang. So Dr. Yang, I am going to kick it over to you and let you introduce yourself and go over the agenda. So Dr. Yang, over to you.
Okay. Hello, everyone. Thanks, David, and thanks, IEEE Standards Association, for giving us this great chance to take this webinar. I'm Yi Yang from State Grid, Jiangsu Electrical Power Research Institute. And some of my colleagues and my teammates are just sitting beside me in the same room, and they gave up their personal time to join us to support the webinar. And they will maybe help me to answer your questions after the webinar, and thanks them as well. Today, my topic is Unified Power Flow Controller, UPFC technology and project application. So my topic includes the following 4 parts. The first part is background, the background for the facts and the UPFC. Okay, as you all know, the facts has been widely used to improve the power system stability and operating performance. With based on the variety of high-speed power electronic devices. The concept of the UPFC was firstly presented by Dr. Jayaji from Westinghouse Science and Technology Center in 1992. It was able to control the power flow and voltage, as well as promote the system stability. It's the most flexible, powerful, and complex factory equipment up to now. But you may say it's also the most expensive one. Yes, it is not cheap, but it is worthy, So I would like to show you our application experience in this webinar. Fax devices can be classified as parallel, series, and hybrid fax. The typical parallel fax include the static VAR competitors, SVC, static synchronous competitors, STATCOM, and others. So normal series fax contains the thyristor-controlled series competitor, TCSC, and the static synchronous series competitor, SSSC, and others. The UPFC as the highest level of hybrid fax is a combination of STATCOM and SSSC. The SVC and STATCOM, can realize the functions of reactive power compensation and voltage control by adjusting the output of capacitive or inductive current. But when the voltage drops, the SVC will face a problem with the shortage of compensation capacity. The STATCOM can address this problem. The TCSC is the first generation fax equipment based on the conventional series compensation technology for power flow control, as well as improving the system stability. The SSC is based on the VSC, the voltage source converter for power flow control, by increasing or reducing the induction voltage. The parallel compensators such as SVC and STATCOM can effectively produce the reactive current and compensate reactive power in the system. So they are used to maintain the load voltage, but its ability to support the line voltage is weak. The series compensators, for example, TCSC and SSC, can effectively compensate transmission line voltage and control power flow, but it is not good at reactive current compensation. A UPFC is a combination of series and parallel device, so it can easily control the voltage, impedance, and the phase angle, making its function the most comprehensive. The UPFC plays a significant role in power grid operation because of control functions such as power flow control, static stability improvement, and reactive power and voltage control, and so on. The part 2, the UPFC technology and application. Okay, so let's review the basic structure of UPFC. The UPFC consists of a parallel part and a series part. Its core equipment is voltage source converter, VSC. So it can operate in series mode and a parallel mode. The parallel converter is connected to the grid by a parallel transformer and controlling the DC bus voltage and the output reactive power or connection point voltage. The series converter is connected to the grid by a series transformer. It can be equivalent to a controllable voltage source and able to control the active and reactive power in the line precisely. So in terms of the core equipment of UPFC, in addition to the VSC converter, series transformer, and parallel transformers, the control and protection system plays a significant role in the UPFC system. So the bypass equipment is also the important protective device in series side. According to the system requirements, 4 kinds of functions can be chosen for the UPFC controller. The first function, the voltage regulation, so which only changes the voltage magnitude, don't change the voltage phase. The second function, series compensation, is equivalent to the capacitance or the reactance. The third function, is the phase regulation. In this regulation, only change the phase of voltage and keep the magnitude as the same. Last one is synthetic power flow control, which is a combination of the above 3 functions. Actually, the development of UPFC technology is with the development of high power and fully controlled power electronic devices. It can be divided into 2 stages. The first stage, the 3-level converter with gate turn-off thyristor GTO and multiplex topology are used for the VSC. In the second stage, the modular multi-level converter MMC with interlaced gate bipolar transistor IGBT is used. So MMC contains a number of submodules which are cascaded and easily expanded. So the advantages of a volt converter valve enlightens the development of technology and application of UPFC and provides a foundation for new generation UPFC projects. So nowadays, 4 sets of UPFC projects are put into industrial operation. 2 of them are in America and another one in South Korea. I think the biggest difference from Chinese projects with others is the converter technology. We use MMC rather than 3-level converter, and we use IGBT rather than GTO. So currently, new MMC-based UPFC technology is widely considered and applied in real projects. In December 2015, the first MMC-based UPFC in the world was put into operation in Nanjing 220 kV grid, China. And the UPFC in Shanghai, 220 kV substation was put into operation in September this year. And the UPFC in Suzhou 500 kV grid will be put into operation in December this year. So at that time, at the end of this year, there will be 6 UPFC projects around the world, and half of them are MMC-based UPFC projects. So we call it new generation of UPFC projects. For part 3, new generation UPFC projects. Since the natural distribution of power flow and a limited control capacity in AC grids, there are several, problems there. Firstly, the unbalanced power distribution of transmission channels limits the power supply capacity. Secondly, the poor controllability and the less flexibility of operation. Thirdly, it is more and more difficult to construct new transmission lines, especially in urban areas. So it needs to use potential ability of power supply of current transmission lines by power flow control. On top of that, we would like to control the voltage and the power flow more flexible using new technology. Last but not least, a new generation UPFC has advantages of high reliability, compact structure, small occultation, and fast adjustment of power flow. We carried out researches on the whole set of UPFC technologies, such as modeling and simulation, primary equipment, control and protection, and testing. In terms of the modeling and simulation, we have carried out electromechanical transient modeling and simulation, electromagnetic transient modeling and simulation, as well as real-time simulation using RTDS. If you are interested in this research area, please refer to our English book for the detailed information. I will show this book to you later. In this webinar, we'd like to more focus on the UPFC project application. Yes, we have successfully applied these key technologies into practical UPFC projects. One of the application scenarios is Nanjing Western Grid, which covers the heavy loads in the Nanjing city. Before the project was put into operation, power was supplied mainly by the 500 kV Nongwangshan substation and Dongsanqiao substation from north and south. But there are some serious problems with Nanjing Western Grid. The main power transmission channel of the Western Nanjing power grid has a seriously unbalanced distribution of power flow, especially the severe N-1 overload of transmission line from Xiaozhuang to Xiaguan and the transmission line from Xiaozhuang to Zongyangmen. So, which will affect the overall power supply and its safety and reliability. If we use the conventional ways to deal with this problem, we needed to construct more transmission lines, but it will take a lot of money, and it's very difficult to take over enough land and space for constructing the new lines. In short term and long term, we hope to control the power flow into two directions. So in this case, we believe the UPFC is one of the best choices. So after the comprehensive analysis of feasibility and considering the economy effect, the UPFC is finally installed in the 220 kV double circuit lines between Tiebei and Xiaozhuang substations. The series voltage is 26.5 kV. The capacity of series converter is 60 MVA. Exchange active power between AC and DC is more than 40 megawatts. This picture shows the main structure of Nanjing UPFC project. So we designed the multi-port topology with 3 VSC in order to achieve double-line power control. The 3 VSCs are connected back-to-back, with a common DC bus by switches. For series side of the UPFC, the 2 VSCs are connected to the double circuit lines between Tiebei and Xiaozhuang substation by series transformers. Moreover, some connection switches are set up to transform the operating mode between parallel and a series of VSCs. And the VSCs are back up each other, which is beneficial to improve the flexibility and reliability. So for the parallel side of the UPFC, the VSC is connected to 235 kV buses of Yanzi substation by 2 mutual reserve transformers. Actually, this picture, this is a video, I think, but it doesn't work now. Anyway, this picture shows different operation modes of UPFC. There are 5 operation modes double-line UPFC mode, single-line UPFC mode, STATCOM mode, double-line SSSC mode, and single-line SSSC mode. This is top view of the 220 kV UPFC in Taipei substation, China. The blue frame is the UPFC area, which includes the valve hall, series transformers, parallel transformers, and the red box shows the GIS area. This is the control center of the UPFC. So in terms of the MMC converter valve in Nanjing UPFC project, the rated capacity is 60 MVA. The number of bridge arm submodules are 26 plus 2, yet 2 for redundancy. Compared with the 3-level converter, MMC converter has some advantages of valves. It has, a compact structure and a small occupied area. The module converter valves are easy for operation and maintenance. And it can reduce the loss of converter valves to 1% of the rated power. So as for the series transformer, the connection mode is 3YND mode of connection. The primary side is 3 series windings. The secondary side is YN, and the balancing winding D supplies the circuit for the 3N harmonics. The capacity of the UPF, the series transformer is 70-25 MVA. Well, the overcurrent and the overvoltage tolerance ability of power electronic devices is not strong enough. For example, when the fault is not happened on the line, the series transformer and the converter may bear large overcurrent and overvoltage. So we use bypass equipment to protect them in fault scenarios. The bypass switches consist of thyristor bypass switches, TBS, and bypass breaker, BBR. The TBS can bypass the converter in less than 5 milliseconds when the fault happens. Then later, the BBS will turn on in 40 milliseconds. After that, the TBS will turn off. At this time, the BBR bypasses the converter and the series transformer. The TBS is able to separate the transformer and the converter. So when the fault happens, so the TBS is the key device to protect the UPFC. In terms of the UPFC insulation coordination, we proposed a raster protective scheme. Here lists the 3 basic principles when selecting the arrestor arrangement for the UPFC. For example, overvoltage generated on the AC or DC side should be limited by arrestor on the AC or DC side, respectively. For overvoltage within the UPFC, critical components should be directly protected by arrestors close to the component. So based on the above principles, the MMC UPFC project is divided into 6 areas to arrange arrestors as shown in this picture. And to ensure the safety of the equipment under overvoltage, the withstand level of equipment isolation should be higher than the protective level of arrestors. In addition, the insulation performance of the equipment is affected by many factors, such as aging of the insulation material, weather, the high altitude, pollution, and so on. So a coefficient of more than 1 is needed between the required isolation withstand voltage of the equipment and the protective level of the arrestors, so-called isolation margin. So selecting a suitable insulation margin will save investment, but also ensure the security and the reliability. So according to the above principle, the insulation margin of a UPFC is shown in this table. For example, for the VSC and the TBS, the isolation margin is 1.15. Control and protection system is the brain of the UPFC system, which realizes control, monitoring, and protection of the whole system. And the base UPFC control includes the control of parallel converter and series converter. The control of parallel converter consists of DC voltage control, AC voltage control, and the reactive power control. So while the control of series converter as the core of the UPFC control contains the active power and the reactive power control, it can also control the DC voltage in order to, suit the application of SSSC. Both parallel and series sides include start-stop control. The line power cannot be directly calculated by the power of UPFC converters. So we take the line power flow as the control target and choose the line voltage as a synchronous voltage. In this way, the double loop coordination control strategy is implemented based on the line power out loop and converter current inner loop, which realize the independent decoupling control of the active and the reactive power. The key techniques of control mainly include the power control of line or section, the power transfer of controlled line N-1, real-time operation optimization, and AVC coordination control. In normal situation, the operation of the UPFC is optimized according to real-time status of the grid. The section or the line power is precisely controlled by the dispatching orders from the control center. In addition, the coordination of the parallel side AVC and the series line power control ensure the stability of the voltage. So when a fault of supervised line N-1 occurs, the emergency control is used to limit the power of supervised line. If a fault of controlled line N-1 occurs, the power transfer of the controlled line will be used to mitigate the power shortage before and after the fault. So in terms of the UPFC protection, we present a comprehensive protection scheme for the UPFC and its access system. So firstly, the range of the UPFC protection covers the converter area between parallel transformer and a series transformer. The parallel and series transformers are configured with the transformer protection. Secondly, the fault in AC system is cut off by AC relay, and the UPFC should be isolated immediately when fault occurs in order to protect the UPFC equipment, especially the converter and the series transformers. An automatic restart strategy for the UPFC is configured to realize the fast regulation function of the UPFC, so after the system fails. Yeah, this picture shows the coordination of the UPFC protection, the line protection, and the bus protection. If the action of the series transformer protection happens, both of the line closing and the converter are blocked. If the action of the parallel transformer protection happens, the UPFC will quit operation. The action of the line protection will block the converter in series side of the UPFC. The action of series transformer protection or UPFC protection will close the bypass breaker. If the bypass breaker cannot be closed or the fault cannot be cut off, line breakers will trip off and the break fail protection will be triggered. So before the UPFC project is put into action, we need to carry out many kinds of testing, such as closed loop test by RTGS, valve test, subsystem test, and system test. So we carried out the StatCom operation test The left bottom diagram shows the result of reactive power control test. The right bottom diagram shows the reactive power step test. In this mode, the converter was able to control the reactive power in parallel side and quickly respond to the changing orders. In terms of UPFC operation test, the left diagram shows the result of the UPFC double-line power control test. The right diagram shows the result of line power step test. So from this result, we can see that the UPFC was able to control the line power precisely and respond to the changing orders quickly. Similarly, in SSSC mode, the converters can control the line active power precisely. We took the UPFC steady-state regulation test to verify the system control of the UPFC. Here is the example. Before the regulation, the active power in Xiaozhuang section is 200 megawatts. The active power in north and south scenario, are 340 milliseconds and 640 milliseconds respectively. The control target of the power in Tiexiao section is 100 megawatts. So it can be seen from this picture that the UPFC regulates the power flow successfully. In the section N-1 test, we simulated the trip and overload of the line. Before the regulation, the power of Tiexiao section is 200 megawatts. The power of Xiaoxia section is 326 megawatts. The power of Xiaozhong section is 267 megawatts. From this picture on the right, we can see that after the N-1 from Xiaozhuang to Xiaguan, the UPFC can maintain the power flow from Xiaozhuang to Zongyangmen at 515 megawatts in 2 seconds. So we had to take a lot of tests, but the most exciting test is artificial, short circuit test in March last year. The control and the protection system operates correctly in this test. Since December 2015, Nanjing UPFC has been under operation for near 2 years, so which solves the problem with power flow out of limit and realize the function of two-way regulation of power flow. So we can see the red curve means the power flow of Qingbin section with a limitation of 1 gigawatt. And the blue line, is the power flow of Xiaozhong section with a limitation of 600 megawatts. So in the summer last year, it confines the power flow of Qingbin section in the target line successfully by controlling the power flow of Xiaozhuang section, so which would exceed the limitation at least 10% without the UPFC. Here was the real short circuit fault of line on 2nd August 2016. So after the short circuit fault happened, so after 2.52 milliseconds later, the UPFC protection was triggered. After 2.74 milliseconds, TBS was triggered. And after 37.5 milliseconds, the BBR was closed. After 46.2 milliseconds, line protection was tripped. And after 5 seconds, UPFC was restarted automatically. So the control and the protection system of the line and the UPFC operated correctly. In terms of the economy benefits, the investment of the project is $30 million US, so which saves over 100 million compared to the conventional scheme of building new transmission lines. During the past 2 years, power supply is increased, which saves over 2 billion kilowatts hour. And the increased sale is 16 million. Added profit is 5.8 million. The payback time of this project is 5.2 years. So there are also many social benefits, such as improving the power supply reliability and solving the problem of power grid construction. The first MMC-based UPFC project also attracts many attention from experts around the world, and we warmly welcome you who attended the webinar to visit Nanjing and the UPFC project. I would like to introduce another UPFC project. So why we decide to build another UPFC? Since task problems exist in 2 languages. For example, the power transferring problem, and stability limitation problem in section from Meili to Mudu, when bipolar blocking occurs in Jingsu, ultra HVDC. So to solve the n-1 over current problem in a 500 kV transmission line, the UPFC is installed in the double line from Mudu to Meili. For 500 kV UPFC, 3 converters are used to realize 2-line UPFC functions. The main parameters are as follows, and it will be the highest voltage and largest capacity UPFC project in the world. The UPFC will realize both power flow control and reactive voltage support. This picture shows the Suzhou 500 kV UPFC project. Okay, the next part is the UPFC proposal of UPFC guide. Why we want to propose the IEEE UPFC guide at this time? As we discussed in the above slide, the UPFC project has advantages of compact structure, small occultation, and fast adjustment of power flow. So UPFC can effectively address the issues faced by the development of urban power grid. And MMC-based UPFC projects, have attracted worldwide attention. So moreover, UPFC has broad application perspective all over the world. However, there is no relative standards or guidance on design, function, equipment, test, or operation of UPFC in IEEE. So we believe that the time for establishing IEEE guide for the UPFC has come. Firstly, the manufacturers, have accelerating demand for the specification to guide their design, production, and testing of UPFC. The utilities need the specification of UPFC to provide the guideline for the testing and operation of the UPFC. The guide of the UPFC is of great importance to the internationalization and global application of UPFC. So in order to promote the development of the UPFC in the world, we suggest to establish a series of UPFC guides in IEEE. Currently, we have submitted the following 3 proposals. IEEE guide for the technical of UPFC, Part 1, functions, Part 2, terminology, Part 3, and thyristor bypass switches. Okay, Part 1, functions of the UPFC. This guide proposes technical requirements of UPFC projects, which are suitable for UPFC in transmission or the distribution power grid. The purpose of this work is to specify the technical requirements of functions for the UPFC. And the main content of this part includes the system structure, function requirement with different operation modes, such as UPFC, STATCOM, SSSC, etc. And the performance requirements such as steady performance, dynamic performance, and other performance. On top of that, it will mention the element and the cooperation requirement of subsystems and the test requirements, including the FAT and the SAT. The part 2 is the terminology of the UPFC. This part, will regulate the glossary and the definition of the UPFC area. And part 3 is the TBS. This guide specifies the technical requirements of fast bypass equipment, including TBS and BBR we mentioned before. It refers to the function, performance, cooperation, test, etc. It's suitable to a series compensation system such as UPFC and SSSC. The main content of this part refers to the fast bypass equipment, typical configuration, structure, and the main equipment. And TBS, for example, the structure, function of the TBS, steady state, and transient parameters and determination principles for TBS, and the BBR, as well as test requirements and other requirements. Okay, so we are very proud of what we have done, and we believe that we have the ability to make the significant contributions to the IEEE guide for the UPFC if it is approved by the IEEE. So which is based on the previous research achievement and the practical engineering experiences. We have published a couple of journal and conference papers and 3 books on UPFC in Chinese and an English version book named Unified Power Flow Control Technology and Application, which has been published in July this year by Elsevier. If you want to know many detailed information about the UPFC technology and application, you can, you can get the information from this book. The guide related to not only technical aspects, but also to manufacturers, utilities, and other interest entities. We really need international participation and cooperation, so a technical working group are required. Currently, we already have some entities to support the guide, and we need more potential entities and experts to join us. We also would like to share our works and experiences with experts who are interested in the UPFC around the world. We'd like to invite 2 experts from related manufacturers, utilities, and research institutions to participate. Your participation will be beneficial to promote the development of related technologies and applications. If enough participants are involved in this project, there will be a significant improvement for making the IEEE guide for the UPFC. So if you want to know much more technology and experience about the UPFC project, and if you are willing to make your own and special contributions to the development of the new generation of UPFC, so please don't hesitate to contact us, and welcome you to join us. Thank you for your attention. So any questions?
Yes, Dr. Yang, thanks so much for that presentation. We've been sending you some questions through the chat. Would you like to take those yourself, or I can read some aloud?
So the first question, what drives the ultimate decision to go for a UPFC as opted to go for a combination voltage control device such as SVC and a series capacitor? I assume the combination is cheaper than a UPFC. Yes, we finally we decided to use the UPFC instead of the series capacitor. Although cheaper, maybe it's cheaper. What we have considered is on the application needs. Series capacitors can only increase the line power, but UPFC can increase and decrease the line power, by VSC, especially limit line power to prevent overload after the fault. So this is an important effect of Nanjing UPFC applications. Moreover, the reactive power and voltage support capacity of the SVC is weaker than the Steadicam, especially in the transient process of the power system.
So, Dr. Yang, do you have another question there that you'd want to read aloud?
What are the perspectives for using the UPFS? It's UPFC, right? In distribution networks of 10 to 20 AV. I think the distribution, the UPFC is not very suitable for the distribution network compared to the high voltage network grid, because the structure of the distribution network is is distributed. Yeah, but the application scenario, for example, the application scenario in Nanjing Western Grid is the structure of the Nanjing Western Grid is like is a loop grid, so it's suitable to use the UPFC in this scenario. Is the MMC IGBT valve used for the UPFC different from the MMC valves used in HVDC applications? If so, what are the differences? I think the IGBT itself are the same. I mean, we use the IGBT in the MMC UPFC and also using the HVDC. I mean, the MMC-based HVDC applications. But the working conditions are different, I think, and especially for the voltage working range. Yeah, in a short, it's using the same valve, but in the different application conditions, and they have different control and protection system for each one. Another question: what level of power loss in UPFC? It's very low, I think. 0.8%. Okay.
Dr. Yang, can you take the last question I sent you? How do you coordinate line protection settings with UPFC in-out situations?
Okay, this slide shows the coordination between the UPFC protection and the line protection. I mean, when the UPFC protection includes the series transformer protection, the UPFC control and protection, and the parallel transformer protection. And here, there is some coordination between the line protection and the UPFC protection. So, for example, the line protection will triggered, and the UPFC will be blocked, and the series transformer, the action of the series transformer protection happened. It will send the trigger signal to the UPFC, and as well as to the bypass breaker. If the bypass breaker, doesn't work, I mean, wasn't tripped, and the fault current, wasn't cut off. At this time, the series transformer will send the signals to the line protection and the bus protection, and the break fail protection will triggered. Another question: are you aware there are seminars being conducted on UPFC in some place? Yes. And as far as I know, actually, we are, we have submitted a proposal for the IEEE ST&D conference. We want to organize a panel session talking about the UPFC technology and application. And we also invite some UPFC manufacturers to join us. And we, if it is approved, we welcome people to join us. And in October this year, we also have a webinar in Nanjing. So if you would like to visit the UPFC project and to discuss communication, the technology with us, we will welcome you to join us.
And Dr. Yang, if you want to go to your last slide, it has your email address so people can contact you. Do you want to put that up for them, please? Thanks.
Okay, sure. Another question: a hybrid line consisting have different parameters. So will UPFC will suitable for power flow improvement in such lines? Also, if the fault occurs, UPFC controls the power flow, but if the fault occur in cable, permanent, so voltage will bypass. Yes, I think in Nanjing 200 kV UPFC project, the scenario is we only have it's an overhead line without the cables. So I think it's a good question. In different scenarios, we need to consider the different parameters. But I think it is similar. According to the design principle, it is similar to using the cables comparing to the high header line, overhead lines. If the fault occurred in the cable, the UPFC, the converter will be blocked, and the UPFC will be protected, by the TVS and the BBR. And maybe several seconds later, it will restart automatically again. So I think the MMC-based UPFC can deal with this problem. Yes, does it make sense?
Yes, Dr. Yang, I'm going to close this out if you don't mind. Dr. Yang, I want to thank you again for your presentation today and your colleagues there. I know it's really late on your side of the world, so thank you so much for staying up late.
Thank you, David.
This
thank you very much. Thank you all.
Everybody have a great day.